We want to look at how statistics is used. So I'm going to let Pat Kuby, our Chief Registrar here at the conference, member of our steering committee, introduce our next speaker.
Thank you. Did everyone get one of these? Now it's Dave. You did Dave, right? Okay. As Dave mentioned, one of the components that we've always had, and I say always, we've only done this 2 years, but is the case studies. And what that does is it's nice for us teachers to get some practical applications to use in our classrooms and that. Because you'll notice that the students really take notice when you can tell them how this is actually used. That's what they like the best. Well, that's what we're going to start with today. So this morning we have Bob Boser with us. He's a quality supply engineer from Ortho Clinical Diagnostics. It's a Johnson & Johnson company here in Rochester. And he's a quality supply engineer. And what that means is that the products that come in, the materials for the diagnostics machinery, he accesses them and then sees where they can improve the materials in there. All right, so without further ado, this is Bob Boser.
Thank you. Thank you very much, Pat. It's really a pleasure to be here. If you can't hear my voice, let me know. I woke up last Tuesday morning with just a horrendous cold, and my first thought was, this is horrible. My second thought was, this is great, because I'll get the cold this week. Next week, we have the conference. I'll feel better. Unfortunately, it's held on. So that's the bad news. The good news is most of you are at least 2 rows back from me, so I hope to not contaminate the environment. It's really a pleasure to be here. My interest level on this topic in this conference is really on several levels. First of all, I work in industry, have been a practicing statistician for about 16 years, so I have a vested interest in the future workforce and the education from a statistical standpoint. I also am a part-time teacher in statistics, so I very much appreciated Jessica's talk and stimulated my thinking on ways and methods that I use to teach as well. My co-author, Vince Vezza, was unable to make it here today, but I did want to give credit. We prepared this jointly, and it's our pleasure to be here. The objectives, what we hope to accomplish in the next 40 minutes or so, is to discuss our perception on the uses and trends and application of basic statistics in manufacturing specifically. I'd like to present 2 case studies on the application of basic statistics, and I want to let you know that the diskettes that you have do not have the data from those 2 case studies. It did not make it on the diskettes, but the data is available. I have it with me. We can make arrangements. Either it'll be on this computer throughout the conference. You can copy onto your floppy, or if you let me know that you need the files, I think I have email addresses for everybody here. I can email those files to you as well. The overall emphasis of this presentation is to focus on the graphics, looking beyond the formula. And what we'd like to do is I'd like to give you a little bit of background on who Ortho Clinical Diagnostic is, talk about some of the applications and trends in manufacturing that are stimulating, well, I think, stimulating the use of statistics, present a very generic process for analyzing data. Excuse me. And the main reason for doing that, there are many available, the main reason for doing that is simply provide a vehicle for going through the 2 case studies. One dealing with an instance of measurement bias, where we were measuring, as a customer, we're measuring some parts, and our supplier was also measuring some parts, and our answers didn't agree. So how we address that, and actually that's still going on. We'll look at that as a case study, and then also another instance where we had some supplier issues where some parts did not meet our requirements, and what we've done to address that. And then we'll summarize. Let me just mention Jessica's point about summarizing all things in 3 or fewer bullets. If I were to summarize my message here today, or our message here today, the 3 things would be: number 1, always plot the data; number 2, always plot the data; and number 3, always plot the data. So simplify it even one step further. And that's really the message of the late, great Ellis Ott, and as a practicing statistician. So if you remember 1 thing or 3 things as a result of this, please let that be it. We are a Johnson & Johnson company. We're one of about 168 Johnson & Johnson companies. We provide professional diagnostic products to hospitals, labs, blood donor centers. We have manufacturing operations here in Rochester, New York, and also in Raritan, in the UK, and also Germany. The focus here in Rochester was formerly a division of the Eastman Kodak Company, and we were purchased by Johnson & Johnson about 3.5 years ago, and then later last year we were merged with another Johnson & Johnson company. Our manufacturing operations involve a wide range of technologies. This is one of the analyzers that we make. Basically, if you go to the doctor or to the hospital and get some blood work done or some assessments of some drugs that you may be tested for, glucose, cholesterol, those type of things, in the Rochester area, it's very likely that those tests will be done on one of our analyzers. This is our Vitros 250 analyzer that runs about 250 tests per hour. Technology, one of the technologies is that your blood sample is spun down and separated into blood serum, and the blood serum is placed in a test tube on this analyzer. The lab technician punches in what tests are desired, the analyzer does the rest. Basically places a drop of your blood serum on a little chip about the size of a postage stamp, and based on what it is you're interested in, however concentrated your blood is, let's say glucose, it'll turn that chip a certain color, and the darker the color, the more glucose is in your blood. The analyzer then reads the chip and converts that measurement into some level of glucose concentration, for example. Our operations involve assembling these analyzers. It also involves chemical and coating processes. I'm not going to talk about that. The case studies that I'll be discussing involve a couple plastic parts that are used on this analyzer, and I'll show you those and discuss those in just a few minutes. In terms of some of the applications or the ways in which statistics are used, in our industry at least, the first of which being incoming materials inspection. We, in the analyzer assembly area, we actually don't manufacture, we really assemble, so we buy parts, thousands of different parts. We have about 4,700 different unique parts that we use in our analyzers. We buy those parts from suppliers. So in many instances, although we're trying to eliminate our incoming inspection altogether, in many instances we're still relying on receiving a batch of material from a supplier, us assessing that material and determining whether or not the material is acceptable or not. In many instances, we're using basic statistics to measure what the mean of a batch is, or the average, or the variability of a given lot, and we're testing versus some specification where the specification is expressed in variability, or is the average has to be within this range. Another application is process and product validations. We are a regulated industry. We're governed by the FDA's quality system regulations. Any substantive change we make to our product or to our process requires a formal validation. The FDA has pretty specific guidelines about validations. Validation is a documentation of evidence that the change you have made does not cause any harm, does not cause any worsening of the product that you're making. The use of statistics is very important in that because we have to show that the new process behaves as the same or better than the old process, and we have to use statistics and use data to show that. So we have to have a proper design in terms of the experiment, and then also proper analysis. We also test our product before shipping. In the testing of our product, the analyzer that you had just seen, for example, many of the release criteria are based on, for example, we'll run 50 glucose results, and we'll look at what the average of those results and what the variability of those results are, and the release of the analyzer is based on that test. So coming up with and deciding what limit should we use, it's really a test for means or a test for variability. The derivation of the limits and so forth are very much founded in basic statistics. Process and product improvement. Almost any manufacturing operation these days should have, if it doesn't, should have ingrained in it a continuous improvement environment. And towards that, there are constantly changes that are made, and a decision needs to be made as to whether or not those changes are for the better or for the worse. Guiding the assessment of that, as well as trying to get in and find out what's the root cause of this problem. Problem analysis also is another application. Statistical process control. I'm not going to get into details of this, but other than to say this is a way in which processes can be monitored. The hope is to, first of all, figure out what range do you expect the process to operate within, let's say in terms of an average. Where should the average fall if everything is going well in this process, what's typical, and establishing limits and using a graphical technique to understand is on a day-to-day basis or hour-by-hour basis, is the process continuing to operate where you expect it to be operating, and to raise a flag when it does not. And statistical process control is a way in which, and based on basic statistics, is a way in which we can do that. And I should mention a lot of these applications involve not engineers necessarily sitting at a desk looking at data, but SPC in particular is involved on the shop floor with operators and assemblers actually taking measurements, using computers to calculate averages, standard deviations, evaluate the control chart, look visually at the information, and help make a decision on whether or not the process should continue or the process should be temporarily stopped and an investigation should be undertaken. Measurement assurance, the last category, that is, what confidence do you have that the measurement systems you're using to obtain the data are reliable, are consistent, and so there are many statistical techniques used to assess and assure that the measurement process is acceptable. I neglected to mention that my objective here is to allow 5 to 10 minutes at the end for questions. If you do happen to have a question that's pertinent, that can be addressed quickly, feel free to raise it. Otherwise, if you could just jot it down and we'll address it towards the end. What are some things that are happening in industry that are impacting the use of statistics? First of all, this is something that's been happening for many years. There are many total quality programs. They have various names that are being used in industry. And actually, this is not only in industry, but other areas as well. The Baldrige Award, you've heard of the Malcolm Baldrige Award. It's a national quality award that's given annually. Up until now, it's been focused on industry and manufacturing. The latest budget does include new additions to the award where healthcare and the education sectors are now going to be eligible for awards as well. So that's very exciting. And because of that, you'll probably be hearing more about the Baldrige Award because colleges, universities, et cetera, will be eligible. This is looking at a model for implementing total quality. And again, I'm not going to go into details here, but one of the concepts is continuous improvement. Everyone has a process, should be monitoring, measuring their performance, and looking to improve performance. These are all things that are contributed to the increase of use in statistics over the last several years. Regulatory requirements. ISO 9000 is a worldwide standard for what a quality system or what are the things that a company should have in place in designing or manufacturing a product. And there's a formal registration process. The FDA has quality system regulations. Both of these are now pretty well aligned, but one of the sections in these regulations includes the use of statistical techniques and statistical methods. And while it doesn't specifically say you have to do this or that, it asks the question, are you using the most appropriate statistical techniques where they should be used? And in terms of applications and auditing, they're asking questions like design analysis of experiments, use of data, the analysis of data, and so forth. So these are also trends or things that are helping promote the use of statistics in industry. Explosion of data availability. Data is everywhere, and probably we suffer from that. It's very easy to generate thousands and thousands of data points from many processes. We're getting data every couple seconds or multiple times a second. Measurement systems now, in many cases, are automatically connected to a computer. So the data's there, it's in the computer. The proper use of that, of course, is another issue, but there's lots of data available and lots of potential uses of basic statistics. Along with that, we have software tools that become more and more friendly over the years. The tool that I'm going to use in the case studies that we'll talk about next, the tool is Minitab. Many of you are familiar with that. We also use SAS quite a bit, but Minitab has made, in my opinion, very good strides towards the ease of which data analysis can be done. These are all things that are contributing to the continued increase of use in statistics in industry, in our opinion. What I'd like to do next is just propose just a general model for analyzing data. And again, the context here is to set up for what we're going to look at in case studies. Each of these points has many subpoints, and there's other things that you can look at, but Just to simply define, first of all, the first thing you need to do is understand what it is you're hoping to do with the data. What's the objective? If you're successful at the end of this study or at the end of this effort, what will that success be? So defining the objectives, of course, needs to be done first. Secondly, obtain data. Either historical data, if appropriate, or collecting new data. Again, you have to match the data to the objectives. So now you have the data, what are you going to do with it? Again, our message here is plot the data, plot the data, plot the data. And Yogi Bear said it best, you can observe a lot just by looking. And in our experience, while there are certainly some very important statistical concepts that you have to start with, concepts of variability, continuous improvement, statistical versus practical differences, etc. Beyond that, I think if we had everybody just looking at the data in some graphical format, very often the answer kind of hits you right between the eyes. And that's really our message here in looking at the case studies. Exploring the data further after you begin looking at it, asking additional questions, following up on outliers, asking, does this picture represent what I'd expect to see? And if not, why not? And digging in deeper. So exploring the data to whatever degree is necessary. Doing a final analysis to make sure that the objectives were met. And then the last point, which is very important, is to summarize the findings. And of course, we need to summarize findings in English rather than in statistical jargon, obviously. It's not acceptable to say, reject the null hypothesis in a final report. And also use, I don't need to tell you that, but also use pictures whenever possible, because very often a picture will convey the solution. Okay, I'd like to present two case studies then. First case study is one on measurement bias. This small tip, it's a small plastic tip, is used in our V-Trail system. Every time a sample is placed on our analyzer, a brand new tip is used, so there's no contamination from sample to sample. And basically, a test tube is put on the analyzer. Our system picks up a clean tip such as this, comes over, sucks up the serum out of the test tube, and automatically goes over and places a very small 10 microliter drop of fluid onto the slide that's then going to be used and incubated and measured. The length of this is very important. We recently are in the process of moving this from one supplier to another. So in that process, we're looking at how is the new supplier doing? A very long process. It's actually taken a year and a half to get to the point now where we've got some new parts from the new supplier. Basically, what we had is a situation, we still have a situation, where we've asked the supplier to provide a summary, a history of a given lot, first batch of material that was manufactured. We received that information. We also asked and requested some samples so we could assess those on our own. In this case, we actually went to another third party, a house that specializes in measurement techniques to measure the length of part of this, and had asked them and hired them to do some measurements for us. Well, as you might imagine, the supplier's results came back and said, looks great. This particular measurement is within specification, and it's a very important measurement to the functioning of our system. The results that we got from our local inspection company said, no, you've got some serious problems. So here we've got a situation, this is very common, where the results that we got disagreed with the results that the supplier had received. So what do? Well, one of the obvious causes that was determined to be likely is there's a difference or inherent difference in the measurement systems. So basically that's where we started from. We said, it looks like the measurement system may be different. Since we had used different samples to come up with our conclusions, what we determined was the objective was to determine if a measurement bias existed between the customer and supplier labs, and actually a little bit further than that, not if a bias existed, but what the magnitude of that difference was. We chose 25 parts, so 25 of these tips, and we're measuring a length of one part of this plastic tip. And we had the supplier measure these 25 results, and we also measured 25 results as well. Independently, I'll just mention there was a lot of other work that's going on as well. For example, if you had the same part and had the supplier using their measurement system to measure that same part over and over again, maybe with different operators, what kind of results would you get? So there were other things that were being looked at the same time. I'm not going to touch on those, but rather just focus on one aspect. And in your handout, you have copies of everything that's being presented, and unfortunately, it's pretty small, so you can't see all the numbers here, but that's not important. Again, the data is available on a diskette that we will make sure that we get to you if you so choose. Basically, what we have then, and this is a mini tab printout, is we have 25 parts, and for each part then we have a measured result as obtained from the supplier's source, and a measured result as obtained from our source as the customer. I do want to mention that these data were transformed so that they don't actually represent the actual numbers, but they're derived from actual numbers. So here's where we're starting from. I'm a very visual person. I have much difficulty looking at a table of numbers and picking out much at all. I know some people can do that very well. It's been my experience that most people cannot, and therefore, again, the focus of these case studies is to look at what graphical techniques can we use. We definitely will look at some of the formulas as well, but what graphical techniques can we use to draw a conclusion from these data? Obviously, 25 samples isn't too bad, but frequently we have much larger data sets, and the challenge becomes even greater to make decisions without plots. What we've done is just to include some different ways in which we could analyze these data graphically. There is no single best way, and probably I think if we could do one thing, it's just to get people to think about plotting, and plotting in every which way. And the experience and the practice and learning the different tools that are available and the ways in which it can be plotted contribute greatly to solving the problem. Here's the first way. This is one way, and that is just a simple scatter plot. For each of the tips, we can plot the result that was obtained from the customer's lab or our lab versus the result that was obtained from the supplier lab. Again, here we're looking at, we're trying to understand, is there a difference, is there a relationship? This probably isn't as helpful as is the next plot, which is to take that same information and say, what would we expect? Well, if we lived in a perfect world, the measurement that we obtained would agree exactly with the measurement that the supplier had made. So this unity line basically represents situations where our results agree exactly. And you can see right off the bat, without even summarizing any statistics, that we have an issue, to say the least. As you can see, in every instance, the supplier's length is larger than the customer's length, than our length is. Just to look at a couple other ways which you could use to draw the same conclusion. Again, there's not necessarily one way, but just to become familiar with the different plotting techniques and try them all. Try plotting every which way. Here we can just plot the 25 parts, and in this case, there's no significance to the ordering of the parts. We're not looking at a time sequence. The parts are pulled randomly. But yet, this does help to show, again, the difference between the two measurement systems. So for each of the part, we have one line representing the customer results and another line representing the supplier results. In this view, we can start to get a visual impression as to what the magnitude of the difference is between the two labs. And one last visual method that we'll look at here is to just simply take on a part-by-part basis and calculate what the difference is between the two measurements, between the two labs. So we can look at that difference or that delta as the supplier minus the customer, and we can plot that again across the 25 parts. So these are just some visual ways in which we can explore the data. Now, right off the bat, you don't have to have a lot of experience in statistics to tell that there's a difference here and approximately what the magnitude of the difference is. We can take it a step further, though. If we were to analyze these data using a common statistical technique, there's a number of ways. The most obvious, since we have a part that has two measurements associated with it, this is an obvious case where we can use a paired t-test. So we can do that, and this is an output from Minitab's paired t-test. Tells us summary statistics for each of the two groups, as well as summary statistics for the difference. And I'm not going to get into any of this. I know in some of your breakout sessions later, you're going to look at Minitab. One of the nicest things, I think, and I have no stock, by the way, in Minitab as a corporation, but one of the nice things about the latest version of Minitab is that associated with each of the statistical analyses, there's an options button that will lead you or give you some guidance in what graphical tools you may want to use, and you can just click on those buttons. And at the same time as you're getting the statistical output, you're automatically getting a graphical output. So there's some guidance there given. In this case, I'm actually not, I don't recall if the probability plot comes out, and I know the next three do. Let me just talk briefly. Looking at those deltas, Minitab has a very nice normal probability plot. Again, I think I share the same opinion as many of you and Jessica, that you don't necessarily need to these days understand the formula for doing a normal test, a normality test, but rather how to do it in Minitab or another software package and how to interpret the results. And this is the output that comes automatically from doing a Minitab paired t-test. So if you're not sure what to do, Minitab's guiding you says you might want to look at a histogram of those differences. So this is a histogram of the differences, so difference on any given tip between the two customer sites. Also shows a 95% confidence interval on the mean, all plotted on the same plot. Another option in doing a paired test is a dot plot. So I won't talk about the applicability of one or the other, but in any event, we've got a dot plot with confidence interval for the mean as well. And those come automatically, as does the box plot. So choose your weapon, but the nice thing is that in many of the Minitab statistical techniques, they give some guidance in terms of what graphs or what plots you might want to use. And I've found them to be very appropriate in all cases. Summarizing the findings, did find that the supplier's measurement system was biased on average about 0.82 units higher than the customer's measurement system. So taking the same parts, measuring them in two different measurement systems, we did confirm that there's a bias, so that was believed to be the difference between the prior assessment of the first lot that was manufactured. We can go further to state a confidence interval between 0.79 and 0.86, which is 95% level of confidence. And then also, whenever possible, if you can throw in a picture to help show the results. Obviously, you have to think about your intended audience, but more and more people understand what box plots are. I can think of very few instances, at least in our company, where I presented some data and I've said, does everybody know what a box plot is? And everybody does. Most people do these days. So, again, there are many other factors that were considered along with this case study. This hopefully gives you a little bit of idea of one application of statistics, and again, the power of using graphs. What I'd like to do next is to look at a second case study. It happens to also be a plastic part. This is a plastic tray, and basically when our analyzer is designed to measure creatinine, let's say, in a certain range, if you happen to have a result that's outside of that range, it's very high, well then what we do is, and our process is optimized for a certain range, then we do an automatic dilution of that sample. So our analyzer will go in and get a sample of your blood serum, and it'll dilute it with a diluent. So it'll go over to another area, suck up some diluent, and it'll mix them up. And it mixes it up in these little disposable trays. These trays sit on a track on the analyzer the operator loads on. So there's a steel track, and these all sit in queue waiting to be used. But we had some concerns in the field where these trays were being jammed in the analyzer. So these sit, if you can imagine this sitting on a track, and the analyzer automatically moves it down into position. It becomes wedged in there, it becomes sandwiched. And these were instances where analyzers that had been used for years did not have this problem. One of the several suspicions were raised in terms of the likely cause, and one of the most likely causes that was thought maybe the width of this tray is too wide. It's outside of our specifications. So the objective then of this case study, this analysis, was to look at the width of these trays relative to the specifications, and if needed then, to improve that process. Again, these were provided to us by a supplier. In this case, it was, the first case the supplier was in the United States. In this case, the supplier is in Germany. So many more difficulties in communication, etc. were experienced. 192 trays were pulled from recent inventory, and just for reference purposes, we call this month 3, and we randomly looked at the width of these trays. So we have 192 pieces of data, pieces of information. Here's the histogram, again, basic plot. One thing that's been added here are the specifications. So we'd like, and we required of our supplier, that the width of this tray be in a certain range, as indicated here. What do you think? Would you agree there's a problem here? So again, without even using any statistics, just comparing sample versus requirements in the picture, we know that we've got too many that are outside of specification. We also can look at things like shape and preaching to the choir here. But basically, you look at, it looks like there may be bimodal or multimodal distribution here. And actually, if you look at this, and any plastic part just about that you find in life has a little number on it. And that little number is a cavity, because when plastic parts are made, very often, sometimes they're made one at a time. So one part's made, it's spit out, another part's made. Very often, though, multi-cavity molds are used. So in this case, there are 8 of these trays that are lined up in a grid, and they're punched out at once. They're punched out into a flat sheet, and then in this case, a secondary operation comes down and cuts all the cavities apart. But for reference purposes, this, for example, is cavity number 7. So for reference purposes and for troubleshooting, etc., we can go in and say, you know, is there a difference between, well, we know we've got a problem here, could it be cavity related? So again, here's where we're exploring the data. First of all, looking at a normal probability plot. Based on this, we know if the histogram didn't hit you between the eyes hard enough, normal probability plot, which probably wouldn't even be needed in this case, but we'll confirm that we may have some issues here. What was done next then is to look at these data on a cavity by cavity basis. There are 8 cavities, as I mentioned. Okay, here we're looking at it a little bit differently, but we've got the specifications for reference purposes plotted, and then we're just looking at a box plot for each of the cavities. What do you think? It's pretty obvious. Again, we're exploring, we're looking for ways of, for explanations and ways to summarize the data. But we've got a problem, definitely we've got differences from cavity to cavity. And that, by the way, is normal. It's normal in manufacturing. It's very rare to build a tool that makes multiple parts at once where every cavity is exactly the same. So we know that, we accept that. The only issue is how close do they have to be, and is it acceptable? In this case, obviously, this is not acceptable. You can see, I'm sorry, cavity 4. And also, you can see we have some other differences. And you have to ask the question, well, what if they were able to move the whole population down, the whole distribution down? Would it still be acceptable? I'm not sure. There are ways of analyzing that, but I'm not sure that's the answer. So what we ended up doing was to review these data with the supplier. It was very difficult. We had to do it through a phone conference, basically, where we sent them the information, the plots, etc. Did agree that there was an issue. There were a lot of issues about whose fault it was, actually, because they use tools that we purchase. It's not always cut and dry. Because the supplier made it, it's their fault. No, it's our tool. It was only built to manufacture a certain quantity, and we're well over that. So, you know, you're not going to get more. So they wanted more money to improve their process from us. So So what we basically said was, well, why don't you see what you can do? See what you can do with the current process. And actually, as you'll see, so we then obtained a second sample. We called month 9 here. And the issue then is, has the process improved? Again, we're kind of behind a black curtain here because the suppliers, in this instance, is not the opposite situation because we didn't know exactly what they were going to do. We had some suspicions. They said they were going to play with this parameter and that parameter, and what they ended up doing, we're not 100% confident. Not the best situation. In any event, this is what the new, improved process looks like. Is it better? Yeah, it's much better. Again, we're just looking at a simple plot, histogram versus specifications, can help us determine that. Do we still have some multimodal situations going on here? Yes, we do. But again, if we look at it, I popped box plot, we've got different cavities, so what we end up with actually is a mixture distribution here. And the analysis we could talk a lot about, but just using some plots to say, is this a better situation? Comparing before versus after, this is what we looked at before from a box plot standpoint. Here's what the after looks like, so it's much, much improved. Now the issue of maintaining that performance is another topic. But in any event, you can see we haven't really summarized any summary statistics to draw a conclusion. We do very often need to go further, but at least we've got a good idea of before versus after and what's happening through some very simple pictures. Okay, what I've shown here is one of Minitab's available analyses. This is a process capability analysis. It puts together a histogram with specification limits and also has many summary statistics, many of those that are covered in basic or introduction statistics, some that are not, some that are used in quality control. And the purpose is not to go through that, but just to mention there are some metrics here that are used, some estimates of parts per million defective. Of course, those estimates are based on some assumptions, normality, etc. So this is just to let you know that one approach would be then, this appears to be acceptable, but somebody wants an answer. Somebody wants to know what's the before parts per million defect rate versus the after. And do you just assume normality to get a quick answer? Probably not. So just to let you know, you might want to look at this as 8 different populations, one for each cavity. And here's a summary of the entire distribution as well. One question may be in this situation is, now that we have a new population, basically new process, change process, is the average of that process on target? So we can look at the target with the transform data is 149.3. Do a simple t-test here. The t-test does come back and say there is statistical difference, but again, next question is what's the practical difference? So this is just a footnote, is this difference of 0.04 wasn't a practical concern. So for all intents and purposes, we're happy that the combined process appeared to be more centered than it was before. Or I shouldn't say that, appeared to be centered versus the target. Okay, in the interest of time, I'm just going to go on to the summary. Tray width was deemed to be unacceptable. Cavity differences were observed as a result of looking at the first sample that we had looked at. Supplier did make some changes, and those did appear to result in improved performance. And also, once again, as with the first case study, there were other activities that were going on. Looking at, I mentioned that this all began with field jam performance problem. So there's efforts to monitor what's going on in the field with these changed parts. And again, you have these data available to you. Have them on this computer, or if you just want to let me know, I can email you those as well. I regret that I can't stay beyond lunch today, but I will be available through lunch. Just to summarize that, use of statistics in manufacturing is growing, and there are many things that we talked about that are impacting. I think, and for the most part, all good things that are really requiring an increased understanding of statistics, or more specifically, increased awareness of how to look at data. Again, if you remember 1 or 3 things from today, The data analysis steps are very important. Plot the data, plot the data, plot the data. And also, in general, graphic analysis can play an important part in looking at and learning from data. So I thank you very much. We've got just a few minutes for questions.
Pat, just to follow up on what Bob was saying, I received Bob's data sets the hour that I came back from finishing the book with the disk. The data sets that he is talking about are on our M drive. I have a set of instructions for you so you can copy all those data sets onto your disk before you leave. I have a blue page, it's all prepared for you. I don't have to have it in my hand right now, but I'll get it to you right after lunch. So that anytime you're at a computer, in any of your sessions, if you want, you just, all the locations and everything are there, you can copy it over onto your disk and you'll have it. I have this set of data listed as an Excel file, and I have it listed as an mini-tab file. Either one will read the other, and almost everything else will read both of them anyhow. So, okay? So we have it, Bob. We've got that corrected for you.
Great, thanks, Tom. Yes?
Take your email address.
Yes, it's actually listed on the form. It's
It'll be on your participants list that you'll get tomorrow.
Oh, okay.
All the speakers, all the participants. As you checked in today, you were proofreading your addresses and stuff. I will reassemble that and we will distribute a complete list. That's part of our networking concept, and everybody will have a complete list of all speakers, addresses, and everything.
Yeah, I think phone numbers in there as well.
I did not include phone numbers. No.
If not, I have a business card I can give you too if you want to talk beyond. Yes?
I was wondering, as a teacher, do you feel that the change in the textbooks is moving in the same direction as the change in the business?
I think so. I use Moore's textbook, Teaching Concepts, and I like that a lot. I'm very interested in looking at Jessica's book. I think there's a lot of good things that are going on. That I frequently look at the Chance webpage, which is, I can't really recall what university that comes out of, but basically they provide a continuing list of examples and exercises and things. So I do see some very positive changes that are going on. I do want to say though that, and Carl Wettstein, who you're going to hear from later, can share his comments as well, but I think that industry also is a little bit behind, or not also, but is behind in applying some of the things that Jessica and others are going to talk about. All too often, industry courses on statistics still are dealing with picking balls from urns and rolling dice, and you're going to hear much more from others on their thoughts on that. But I do see academia and I see industry moving in the right direction, but there's still quite a ways to go in industry specifically. Other questions?
Do you find you're reporting to the corporate equivalency non-statistical people that they're understanding your displays that you're using? You say plotting.
I find that they understand plots much more than they understand a confidence interval or.
So you're using that kind of display?
Whenever I can use a plot to tell a story, I do that and show the plot, and then usually a lot of times there's someone who has more in-depth statistical knowledge, and so hearing yes, there is a statistical difference or this is no different, whatever, also supports it. But hopefully, I always try to find a plot that tells the story. Okay.
Okay, well, we appreciate the time you took to put this presentation together, and thank you for coming back.
Thank you very much.
Now for the complicated part of our conference. We're going to break up next into our first session, session number 1 on the bottom of page 2. This is one of our group sessions, and each of you have been identified by color and by letter as part of a group. And so that we're asking you to follow your group to this next session, to the rooms that are indicated. Building 11 is across the courtyard in the back. It can be entered from either end. The 100 rooms are on the first floor, the 200 on the second. And we'll move there, passing the refreshment room and restrooms if you'd like. Let me announce the hosts for these sessions. The Bluebirds, Group A, will be hosted by Lori Judd. Lori, Lori's right here. Let me say this about Lori. Her mode of operation is something we most commonly try to emulate.
Lori, stand up, I can't see the name tag.
Not everybody's tell them, look at their name.
Look at your name. If that's the same name as you are, then the color is right. Red, green, or blue. Anything else I got to say about that? Okay. Lori, with the Bluebirds, Group A. Group B, Kim Martello, the Greenbirds. Kim is just a standard deviation away from the Hall of Fame in statistics lingo, and she'll be leading Group B. Okay, thank you, Kim. And the Redbirds, Pam Keys. Pam is an outlier with us who knows no limits. Okay. We'll now take ourselves in the general direction of east toward our conference room.